In this video, we're going to continue to look at some introductory quantum mechanics ideas for general chemistry students. And as a consequence of Max Planck's introduction of discrete energy in his solution to the black body radiation problem, we're going to look at some of the consequences in terms of the structure of an atom. Atoms are complicated, and historically and contemporarily, one of the easiest ways to introduce these ideas of discrete energy levels is to consider a confined electron to confine an electron in a box. So we'll look at the particle in a box. So what do we mean by a box? We mean an infinite well, or a well with infinite potential energy walls. So the box, we don't need a lid on because the walls are infinitely high. So let's imagine we have a wall here. We have potential energy increases that way. And we have another wall here. So to get out of the box, so these walls are impenetrable. To get out, you have to go up. Let's imagine that the walls are infinitely tall as well. So in short, you cannot get out. Let's imagine we're just looking at one dimension. Let's, for argument's sake, say it's the x-axis. And we have an origin, 0, and a length, let's call L. For now, 0 and L are just labels. So I can go from the wall labeled 0 to the wall labeled L and go back again, for example. And let's make a statement. So to exist and persist in the box, the wave function of the particle, or the mathematical interpretation of what exists in that box, which we'll call the wave function. The wave function of the particle in the box must have a wavelength given by the expression lambda is 2L over n. So let's write that down. So to exist and persist in the box, let's say the electron, because ultimately we're interested in an electron in an atom, but we're going to consider for now an electron in a box. So the electron, and when we say the electron from now on, actually, when we say the electron, we mean its wave function. Which has the symbol psi. So psi is pronounced psi. Okay? So to exist and persist in the box, the electron actually, its wave function, psi, must have a wavelength. Lambda, which is equal to twice L over n, where n can be 1, 2, 3, etc., and any whole number integer value. So let's try and qualify this statement. Well, let's say that n equals 1. If n equals 1, the wavelength must be 2L. Well, what do we mean by wavelength? So if you consider a wave, which we'll say is an oscillation about a midpoint. Okay, so let a wave be an oscillation about a midpoint. Then the wavelength is the distance between adjacent identical parts of the wave. So it could be the peak here and then the next adjacent peak. It could be the trough here and the next adjacent trough. Or it could be a node. So let's call this a node. A node is where the wave hits the midpoint about its oscillation. So we'll say peaks, we'll say troughs, and nodes. Either way, the wavelength doesn't change. We just have to get to the next reproducible part of the wave. Okay, so what does n equal 1 look like? Well, if n equals 1, it would look like this. So the wavelength would be there and back, so that would be a complete wavelength. So it would be L, 0 to L and then L to 0, so that's twice the length L divided by 1, that would be one wavelength. And essentially, the way I'm going to draw these, we have to hit a node at the walls. The walls have to be a node if the wave is going to reproduce itself. So this would be for n equals 1. For n equals 2, then the wavelength would be, or the wavelength would have to be 2L over 2, which is just L. So then we have to fit an entire wave within L at the n equals 2 level. I'll do one more, just in terms of proof of concept. We'll do n equals 3. So if n is 3, then the wavelength must be 2/3 L. And as you can see here, it is. So n equals 1, n equals 2, n equals 3. What you can probably notice, or at least what's worth pointing out at this stage, is that as the energy increases, as we go higher and higher and higher up, first of all, we have more nodes. So a couple of things I would point out at this stage. The energy seems to be proportional to the number of nodes. A node is just where you hit the midpoint of oscillation. So for example, at the energy 1, we have no nodes, excluding the walls, we have no nodes. At energy 2, we have one node. At energy 3, we have two nodes. So 0 node, 1 node, 2 nodes. So we can see that the number of nodes is the energy minus 1. So energy seems to be proportional to number of nodes. And I would say another important thing, the number of nodes seems to be the energy N, not E, N minus 1. N minus 1, N minus 1, N minus 1. And again, we see this relationship between energy and frequency. Energy is proportional to frequency. Again, because we're using Planck's idea that energy is a number of h nus. Okay, so these are things I would keep in mind as we start to go through the idea of a particle in a box. Okay, so I'm going to erase this board so we can continue our discussion. I have to erase the board slowly so I don't pull the whole thing off the wall. Okay. Okay. So, because it's hard to talk about anything in quantum mechanics without using other concepts that you haven't necessarily introduced, don't worry if I introduce things and then don't tell you where they're coming from. We have to do that, otherwise we'd have to derive everything and then we'd never get anywhere. So one of the things that I'm just going to introduce and not really tell you where it comes from, at least not in this video, is the Devoy relationship, which most people just say Devoy because it's a French word and it's hard to pronounce for some people. So we'll just say the Devoy or Devoy relation tells us that the wavelength is equal to Planck's constant over rho, not rho, P, where P is mv, which is just linear momentum. Okay, so momentum P is just mass times velocity. So this is a relationship between wavelength, essentially, and mass, which is a very important relationship. But the acceptable, because we're confined to a box, acceptable values of linear momentum for a particle in a box oh good, just making sure I'm recording the video. The only acceptable values for momentum for a particle in a box are momentum is h over lambda, so I just solve for momentum, I cross multiply these two. So momentum is Planck's constant over lambda, which equals nh over twice L. Recall that we said on the previous page that the wavelength has to be twice L over n. Okay, so subbing in lambda here, we've got 1 over lambda, so we invert this, so it's n over 2L, and we put it in here. Okay. So these are the only allowed values if the particle is to exist and persist in the box. Now, energy, we can think of energy as the sum of kinetic and potential. So energy we can think as the sum of kinetic and potential. But we can ignore this for our particle in a box because potential energy is position sensitive. We're going to assume that our electron can't get out of that box. So its potential energy is less relevant than its kinetic energy, so we're just going to ignore it. So we're just going to assume that whenever we say energy from now on, it's just kinetic energy. And kinetic energy we know is mv squared over 2. Okay. If I take kinetic energy and I multiply and divide by m, so I just multiply it by m and divide by m, so I'm allowed to do that because I haven't done anything net, just multiplied and divided, then it implies that energy, which is our kinetic energy, is m squared v squared over twice m. Now, we said previously that mv is p. So this is just equal to p squared over twice m. So we've got a different way of looking at kinetic energy in terms of linear momentum and mass. Okay. So we've got energy is p squared over twice m, and p, remember, the allowed values of p are nh over twice L. So from here, we've got the allowed values of linear momentum are nh over twice L. So we combine these two equations together. It implies that the energy of our particle is going to be p squared, which is n squared h squared, over 2 squared, which is 4 L squared. So that whole thing is just p squared. And then I've got a factor of 2m. So if I combine the 4 and the 2, for example, I then got energy is n squared h squared. The 4 multiplies to 2, and I get 8 ml squared. So this equation is a very important equation. It's the energy of our particle in a box, our restrained energy. It's a quantum mechanical value of energy. And let's erase this board and we'll plot what this looks like for our particle in a box. So I'll erase this, try not to pull the thing off again. Okay. So we've got our equation, energy of our particle in a box, where the particle is the electron. But it doesn't have to be the electron, it just has to be a subatomic particle. Energy is n squared h squared over 8 ml squared, where L is the size of the box that the particle finds itself in. Well, this is just equal to Planck's constant h squared over 8ml squared. And we can look at the different values of n, because n are the energy levels as you go up the box that contribute to the total energy the particle can have. N could be 1, so it could be 1 squared. N could be 2, so it could be 2 squared. N could be 3, so it could be 3 squared. N could be 4. N could be 5, etc. So these are all our n's, and we take the square of them. So 1 squared is just 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Okay, so we can start to see how our energies could play out in our box. So here's our box. One, 4, 25, 16, 9, 4, 1, for n equals 5, n equals 4, n equals 1. And what you notice here is, I haven't drawn this to scale, but the separation gets larger. So this starts to fit in with what Planck was looking at with the blackbody radiation experiment. As you get higher up, it gets harder and harder, or it requires more energy to jump to the next one. Because if these are stepping stones, each subsequent stepping stone is further away than the previous one. So it's not a linear scale. So that's important to point out at this stage. Okay, so particles in boxes, this is probably the easiest way for anybody to consider quantized energy. In another video, not this video, but in another video in this series, we'll look at how this fits in with the Schrödinger equation, which will look a lot more complicated, but it will boil down essentially just to this equation. At least for a single electron in a confined space. Let's consider a particle on a ring, and then what we'll do, we'll try and bring them together and unite the particle in a box with the particle on a ring. Why consider the particle on a ring anyway? Well, it's much more like an electron in an atom than a box. For no other reason than it's circular. But we'll see that no matter how you think of it, you get the same answer. Okay, so we'll carefully erase that. So particle on a ring. Okay, particle on a ring. So when we say a ring, literally, we mean a circle. Let's say we start at the origin here. So let's say we start at this mark at 0 distance traveled, and let's say for argument's sake we go clockwise around the ring to a value of 2 pi. So we've gone 360 degrees. And we know that that's equal to 2 pi radians. So once round the circle is 360 degrees, but that's also 2 pi radians, and that's the way we are going to view it now, as 2 pi radians. And let's say the ring has a radius r. If we were to plot this as a wave, we could have 0, 2 pi would be 1 revolution, 4 pi would be a second revolution. So as we go round, it's as if the wave has come back to the origin again, and it could do a second revolution, etc. So 2 pi radians. And here we're going to consider the wave function, which recall is psi, so psi. This is the wave function, which for now just means it's a wave, and there's a mathematical idea behind this wave that we haven't looked at yet, but we will. But for now, it's just called a wave function. Let's make some assumptions. So similar to the particle in a box, for the particle on the ring to exist and persist on a ring, the electron, or now we know specifically we mean the wave function of the electron, must reproduce itself not duplicate, not destroy itself, but just reproduce itself every 2 pi radians. So what this means is, if an electron begins here, it must be ready to begin again at 2 pi radians. It must be ready to begin again at another 2 pi radians. The energy of the particle rotating around the ring, we're now going to look, rather than linear momentum, we're going to look at angular momentum. So the energy of the particle rotating around the ring which we know is E p squared over twice the mass. So this is our kinetic energy from before. Again, we'll assume the electron doesn't really change its net position. It's a fixed position r away from the center, but it's moving, so we're just going to consider its energy as exclusively kinetic energy. But in this case, we have P is angular momentum. Okay, so we're going to consider angular momentum. So I'll have to erase, I'll have to erase this board so we can fit the last page of our argument here. Okay. Maybe I can just get away with erasing this text. Leave the diagram on the board. Okay. So, angular momentum is regular linear momentum multiplied by a radius. So we have to include that. So this will have a consequence for our equation. I just want momentum, but if I'm going to use angular momentum, then I've got energy is p squared r squared, that's angular momentum, over twice m r squared. Another way you can think of it is I've just multiplied top and bottom by r squared. So I've taken my original p squared over 2m and I've multiplied and divided by r squared. And now I can see that this is just angular momentum squared. Divided by twice the mass times the radius squared. So incorporating this into the Devoy relationship, as we did before, the particle in a box, we've got, instead of P is h over lambda, so linear momentum is h over lambda, we've now got angular momentum PR is h over lambda r. Okay. To exist and persist on the ring, though, r must have certain values. So let the circumference of the ring equal 2 pi r. So that's the circumference of any circle. The circumference here just means the length around the circle. So to exist and persist on the ring, the particle's wave function therefore must have wavelengths that are given by the following expression. So from this idea, so linking this statement down here with the following argument, the wavelength, lambda, must be multiples of the circumference, where n can be 1, 2, etc. Okay, so the wavelength must be multiples of the circumference. Okay, so let's incorporate that into the following argument. To do, though, we need to free up some room. So let's free up some room. Okay. So we've just said that, or previously we said that lambda must equal 2 pi r over n, where n can be 0. No, it can't be 0. Well, it could, but it would make no sense to be 0, because then you'd have nothing to talk about. 1, 2, 3, or any whole number integer. Okay. This implies that r, if we just cross multiply this equation here, then r is going to be n lambda over 2 pi. Okay, so I want to isolate r. I just bring 2 pi downstairs, bring n upstairs, and I get the radius r is n lambda over 2 pi. And now recall our energy equation. The energy of our particle on the ring must be p squared r squared over twice mr squared. So just kinetic energy with this angular component, r squared incorporated. And recall also our Devoy relationship, PR is h over lambda r. So we're just trying to get everything we'll need on the same screen. We've got our to exist and persist equation, we've got our energy equation, we've got our Devoy relationship, relationship between angular momentum and wavelength. So if we combine these now, we've got energy So I'm going to square this and then insert it as a numerator here. So I've got HR over lambda squared. Okay. HR over lambda squared is PR squared, so it's my numerator in my equation. And then my denominator is 2mR squared. Okay. So energy is PR squared, where PR is HR over lambda, square it to get the numerator, and then the denominator is twice mR squared. Now we're going to use this equation and insert R into here. Okay? So instead of R squared, we're going to have n lambda over 2 pi squared. So we keep the H, but instead of R, we have n lambda over 2 pi. So that's our R. We have this lambda over here. Okay? And then we have to square the whole thing. So again, we've got h over lambda, but instead of r, we have n lambda over 2 pi, n lambda over 2 pi, and then we square the whole thing because of this square here. And then that whole thing is over twice mr squared. Now you can see we have some common terms that we can cancel. This lambda is going to disappear. So we're left with n squared. We have h over 2 pi squared. And then we have twice mr squared. Scientists have factors of 2 pi all over the place. So a long time ago, smart people, Dirac and others, decided to do away with 2 pi's just by rephrasing them. So we're going to say that h over 2 pi is equal to h bar. So you pronounce that h bar. It's essentially Dirac's version of Planck's constant. We'll use it a lot, and it's just h over 2 pi. So we've got energy is n squared h bar squared over 2mr squared. And that's our quantized energy equation for the particle on a ring, where obviously n can be can't be 0. It can be 1, 2, 3, n. But what we're going to do next, we're going to compare this equation with the particle in a box, and we're going to convince ourselves they're actually the same thing. So we're going to prove that this and the other equation are the same. Okay, so let's erase this page. carefully. Okay, so we're about 40 minutes in. I try and keep these videos less than an hour if possible. Okay, this is the last part of the notes I have planned for this video, so a new title though. So we're not going to look at the particle in the ring, we're going to compare the particle in a ring with the particle in a box. So I'm going to call this linking the particle in a box with the particle on a ring. So the box, recall, we said that energy is n squared h squared over 8ml squared. The ring, we said more recently, was energy is n squared h bar squared over 2mr squared. So there are two equations. And we're going to try and reconcile them, convince ourselves we don't have two things. We're looking at the same phenomenon from two different perspectives, but it's actually the same thing. So for the box, the smallest allowed wavelength of our wave function is twice L. For the ring, the smallest allowed wavelength is the circumference of the ring, which is 2 pi r. So to reconcile them, we know that 2 pi r can be considered the same as twice L. So this is the smallest allowed wavelength for the particle, the wave function in the ring and the box to exist and persist over time. So wavelength must be the same in each. So if the wavelength is 2L and 2 pi r, then 2 pi r must be equal to 2L, which implies that L is equal to pi r, because we can just cancel the factor of 2 from both sides. Let's convert one equation into the other. So we've got the energy of the wave function in the box is n squared h squared over 8ml squared. And that's equal to n squared h squared. But instead of L squared, I'm going to have pi squared r squared. So I've got 8 and m. But now I've got L squared, so it's going to be pi squared r squared. Okay, so just replace an L squared with pi squared r squared from over here. I'm going to factor out this 8. This is equal to n squared h squared over twice m multiplied by 4 pi squared r squared. So if I went backwards again, the 2 would hit the 4 and would regenerate the 8. Why am I factoring out 8 into 2 and a 4? Well, I'm going to try and reconstitute from that 8 that 2. So it makes sense that I would want to have 2 and m together, because I'm trying to convert this equation into that equation. Recall that we said h over 2 pi is equal to h bar. So we can write this as n squared h over 2 pi, h over 2 pi. Okay. So here I've got h squared, so that's just h and h. And then I've got 4, which is just 2 by 2, and pi squared, which is pi by pi, and then r squared. I've also got a factor of 2m here. Okay. So again, my n squared over 2m remains. My h squared becomes hh. My 4 is 2 by 2. My pi squared is pi by pi. And I've got 1 over r squared at the end. Well, this just equals to h bar, right? So I've got n squared h bar squared, and then I've got 2m r squared. So now we've converted the box into the ring, so we can see that these are exactly the same equation. So it doesn't matter how you consider this, whether you consider the box or the ring. I would encourage you to think of the box, because I think the box is simpler. But with just some basic algebra, we can convert one to the other, and we've got an effective way to quantize the energy of the wave function. And we're going from Max Planck's 1901 invention of quantum mechanics, ultimately gearing towards an application to chemistry and the structure of the atom. As we come to the end of this video, a quick recap. So this video has looked at an application or an extension of Max Planck's discrete energy that he came up with to explain blackbody radiation, and it applies it to chemistry. So we know that chemistry is based on the atom, and we know that electrons abound within a potential of the atom. They, of their own accord, they don't leave the atom. They can be removed, but they stay within the potential well of the atom. So to understand the atom better, we have to understand the implications for discrete quantized energy of the electron in the potential well of an atom. And that's very complicated and a very strong stepping stone, at least to consider one electron, is to look at a particle in a box. An extension is to look at a particle on a ring. That will allow us to look at, for example, when we look at atomic theory, look at the Bohr atom and the onion-like rings of the Bohr orbits, the planetary orbits of Bohr's atomic model. But we can see that what we learned from the box applies to the ring and vice versa, because we've just realized that they're equivalent. So that's what we've just looked at, and that will conclude this video.